There's one last tricky thing to deal with when we're talking about these second order constant coefficient homogeneous linear differential equations. Uh, when there's no y prime term or q prime term, if we're talking about the circuit situation, then we always get sines and cosines, as we've seen, and this is just because the characteristic of equation always turns out to be r squared plus k over m equals 0. And so you always get purely imaginary roots to the characteristic equation, and so you always get just a mix of sines and cosines. But just intuitively speaking, if you have a mass hanging from a spring and you set up some initial conditions, it's going to oscillate. But it's going to give you a sinusoidal oscillation, but you might have a mix of sines and cosines like this. So somehow this is supposed to represent just a single sinusoidal oscillation. So how can we understand what the sinusoidal oscillation is? In particular, what is the amplitude and phase of this oscillation? Because it's written in an inconvenient way. So the thing to remember is when you have a sine and a cosine being added together and the inside is the same, it's possible to rewrite that sinusoidal function as some amplitude times sine of that angle inside, which is 4t for this example, plus some phase angle. Okay, and A and this angle that I'm writing phi, these are constants. In other words, they don't depend on t. They will depend on the other values showing up here, but they don't depend on t. So how can we find them? Well, the way to find them is to use the addition formula for sine. So we get A times, so then the addition formula, we get sine of 4t times cosine of phi plus cosine of 4t times sine of phi. Distribute that A to these two terms. So let's just write this A here and here. Okay. Now going back to the original, you can see this 2 right here must be A times cosine of phi. By the same token, this 5 right here must be A times sine of phi. So we get this system of 2 equations and two unknowns, A and phi. And I'll let you solve these equations, but the short version is that the amplitude is the square root of the sum of squares of these coefficient values. So for us, that's going to be what? 4 plus 25, so square root of 29. And for phi, right, now that we know what A is, we can divide both sides of both of these equations by the amplitude, and we get cosine of phi is 2 over root 29, and sine of phi is 5 over root 29. And we can use these 2 equations to determine phi. So you do need both equations because, right, if there's a plus or whether there's a plus or a minus sign on these 2 will determine what quadrant your angle phi has to be in. So for this particular example, since they're both positive, we know that this angle phi is going to turn out to be in the first quadrant, and so we can just use inverse sine or inverse cosine to find what this angle phi is. So let's do that. So I'm going to do inverse sine, make sure I'm in radian mode, inverse sine of 2 divided by, inverse sine of 5 divided by square root of 29. Close off all my parentheses, and I get that phi is 1.19, and that's in radians. So now we know that that original sinusoidal function we started with is square root of 29 times sine of 4t plus 1.19. Okay, so the amplitude is square root of 29, and the phase shift is 1.19. Whether you want to write this particular function as a sinusoid like this, or as it started with the separate sine and cosine, really depends on what you're going to be doing with this function. So it kind of is context dependent, and so you do have to know how to go between the two representations.